This video looks at the idea of Newton's method and how it's used to try to find roots. In this case, we're going to look at the process first, and then from a graphical standpoint, and then we'll look at it from an algebraic standpoint. If you recall, we talked about the fact that Newton's method begins by using a tangent line and looks at where extending that tangent line to a curve intersects the x-axis. Then this point becomes the new point of tangency, and the tangent line is then kind of slid down the curve to this point right here, and then a new tangent line is drawn, and each time the intersection point of the tangent line and the curve start to get closer and closer to this root over here. So that's the idea that we're going to talk about. Let's look at what happened graphically. We can do it on the graphing calculator by simply saying, all right, this is the point of tangency. I'm going to start with my initial guess. This function, by the way, is x squared minus 2. So the solution is really the square root of 2. So we're trying to approximate the square root of 2. So what I can do is I can say, well, my first guess is the square root of 2 is somewhere around 4. Well, now we know it's not quite that far off, but if we started even with a point this far out, it will actually hone in on this actual answer, the square root of 2, relatively quickly. So what I'm going to do is I'm going to actually extend the tangent line. So I plot a tangent line at the point x equals 4, that's my initial guess, extend it down, and then I find where it intersects. So I'm going to actually copy this coordinate, and I'm going to paste it as the coordinate of the tangent line. And when I hit enter, it's going to slide down the curve to a point right above where the intersection of the x-axis currently is. Okay, and as you can see, the tangent line now has an intersection point with the x-axis that's even closer to the root that I'm looking to find. So now I just continue this process. So I take this x-coordinate, copy it, paste it, hit enter. Okay. And each time it gets closer and closer. And you'll notice this 1.42 is getting closer and closer to the square root of 2. You may recognize the square root of 2 as about 1.414. Copy that guy, paste him. Okay. And you can actually almost not tell them apart because unless I zoom in because they are so close. Now I can zoom in. And as I zoom, you'll start to see them separate just a tad. And you'll be able to see that they really are close, but not exactly the same. Okay, and so I could continue this process. Okay, so that's the big idea behind it. Now what would this look like algebraically? Well, here we've got Newton's method kind of mapped out with a sketch. And so I have my tangent line. I have my initial guess of x sub 0 here labeled. And this then would become what I'm going to call my x sub 1 in my first iteration. And so the real question is, how do I find x sub 1? So if you recall, when we looked at differentials, we can actually start thinking of the tangent line as a fair approximation to the actual curve near the point of tangency. So when we get close to the point of tangency, we kind of can use the tangent line in place of it. And if you recall, we called that local linearization. And we said, well, we could actually write the local linearization of it as my jump-off point, we were calling it f of a, plus the derivative, okay, that was the slope, the rise over run, at that point, times the run, which is x minus a, how far away x is from a. So this is my jump-off point. It's where I start on my y-axis. And then this adds or subtracts, depending on whether the slope is positive or negative, a certain amount to that. Okay, slope, rise over run, times run gives you rise. Right? That's the rise, if you recall. Okay, well, if we want to think of this as a local linearization, I can say, well, suppose I'm just going to rewrite this using the notation in my sketch. I'm going to call this f of x sub 0, that's my initial guess for Newton's method, plus the derivative at x sub 0 times x minus x sub 0. So really what we're trying to do is find that x sub 1, and solving this thing for x is going to give us that x sub 1. So we really want to know when this thing hits the x-axis, which is a y-coordinate of 0, so we set it equal to 0. So if we solve this thing, I can say, well, that means f prime of x sub 0 times x minus x sub 0 is going to equal, I'm going to take this term to the other side, minus f of x sub 0. Now I'm going to divide through by the derivative, so that means x minus x sub 0 is going to equal minus f of x sub 0 over f prime of x sub 0. And solving for x, taking the x sub 0 to the other side, and there we have it. Okay, so in this case, what this says is if you give me an initial guess, I can plug my initial guess into this side, and it will give me what I'm going to call my x sub 1. Okay, and then if I want to do it again, I simply repeat it. My x sub 1 becomes my x sub 0, and the whole process continues. So in general, I could actually write this as x sub n is equal to my x sub n minus 1 minus the derivative of x sub n minus 1, I'm sorry, the function at x sub n minus 1 divided by the derivative of x sub n minus 1. And there's a general process for generating these intersection points with the x-axis. Now, let's see what that would look like. So I'm going to go over here, and I'm going to define my function. I'm going to call it f of x. And in this case, I was doing x squared minus 2. That's the one I was trying to find the root for, because the root of that is the square root of 2. And now, if I want to actually do this repeat, if I wanted to continue repeating, I would like to define a function that looks like this. Okay, and I'm going to call it Newton's method. I'm going to call it NM for Newton's method. So I'm going to say define NM of x to be equal to my, here x represents my initial guess. So I'm going to call that x minus, since I've already defined my function f, I'm just going to say f of x divided by, and now I want to make sure I take the derivative of f of x. So let me get my derivative command. Okay, and there's my Newton's method. So now I can go through the process we just did graphically, but I can do it algebraically. So I can say nm of 4, that's my initial guess. There's that 2.25 that we saw the first time we did it graphically. And then I can say nm of, and I can use my answer key, control answer, hit enter, and I get another approximation. Hit enter again, get another approximation. Hit enter again, get another approximation. And I can keep doing this until I really don't see a change. And here's actually the first time we really don't see a change. So within this many decimal places, this is really an approximation for the square root of 2. So it's simple as that. In fact, that's how your calculator operates. It uses an algorithm to try to approximate these when you put them in. It doesn't have them all memorized. So in a nutshell, that's the idea behind Newton's method. And it's a pretty efficient method for finding roots when we can't find them exactly. And most equations, to be honest, can't be found exactly. The solutions can't be found because there are very few equations we can actually do algebraic manipulation and get.